Okay. Now, because you said that low water cut and high water cut, you have to create two fields. So, one company, this Slumberger, I think you know, very famous, very big company. They have one design called Netco dual polarity system. So, dual polarity what system is that you see the left side bottom, you have one electrode, two electrode, three electrode, four electrode. You can create many. Okay, and upper part you see they have given DC, lower part they have given AC. Okay, so lower part means lots of water is there nearby. Okay, so water cut high, water cut high. Okay, they are low water cut. This area, low water cut. Okay, so there you are using DC field. So you are using vertical or horizontal maybe electrodes in low water cut zone, apply DC, but bottom portion separately they are giving AC. So when DC they are creating bigger particle, they will come down to AC zone. Okay, AC zone again there will be collision. Okay, when collision is there, it will create further bigger particle and take water from bottommost portion. Okay. Okay, so okay, so they have given. I have taken from their actually brochure this figure. Okay, so this Natco dual polarity treater, you can see this one AC/DC. If they are applying, their rate is higher, rate index, and if you are using only AC, the rate index is lower. AC conventional electrostatic and they are dual. Okay, uh, so when DC field, it is getting some small bigger particle coming to further lower, it is getting further bigger particle, then it is getting separated. Fine. Okay. Principle of separation. So already we discussed VT formula. This is your universal formula. You have to remember all time. Okay. We say 1.78 10 to the power minus 6 Sg delta dm square by mu. Okay. And emulsion treating, when you are treating emulsion, dm should be larger. Emulsifying agent if is there, then you have to use demulsifier. And settling time also you can change based on your how much hard emulsion is there or moderate emulsion is there or unstable emulsion is there. Based on that you can give settling time. ACTTLING. Okay, you can give settling time. And when you are treating emulsion, you can use heater treater along with your electrostatic treater. Okay, so these are key terms actually. Okay, whatever we are discussing based on all these things. Okay, so gravity settling also part of this one, right? So because of gravity settling, fluid will be falling down. First level, next level, you are separating oil, water. You are creating two layer, and two layer done. And oil, when you are sending to your gun barrel and stock tank barrel, before that you have to remove water sedimentation. So BSW you have to maintain. Then you put your tank. From tank people can take. Okay, refineries you can send to refineries. Okay, we'll go to do some calculation based on. Okay, I'll go to next slide. Fuel cost. So this is actually heat duty calculation. How much heat you are giving. So based on that, actually you can calculate fuel cost. Okay, how much fuel you are, because heater treater you are using without electrostatic separator, then in that case your temperature rise will be higher. So your money for buying fuel will be higher. But if you are using heater treater as well as your electrostatic separator, so both case actually cost will be going down. So how to show that one? So using some calculation we will try to do that. Okay. So flow, you know heat calculation, rho del T Q C, or better I will write in different way. Okay, rho Q del T C, MST. Rho Q means actually mass, right? Rho means density, flow rate, and temperature difference. Q equals MST formula, you can remember, heat equals mass into specific heat into delta T, temperature difference, right, and specific heat. Okay, now you have to know the units also. Here they are using unit as BTU per hour, I think. Density will be lbm per barrel, and flow rate, it will be barrel per hour. Delta temperature difference, degree Fahrenheit they are taking. So specific heat capacity also you have to take accordingly. Specific heat you have to take BTU per lbm degree Fahrenheit. Q unit, okay? Q unit, okay na? Fine. Okay, now using the formula we try to calculate some heat duty. Okay, so problem is that Q oil is given 1000 barrel per day, BPD. Q oil, Q water 500 BPD, BPD. I can write BWPD also. Okay, BWPD also I can write. Okay, many author will be writing like this. BPD, many author can write BOPD also. Okay, so don't be confused, it's all the same. Okay, I can write barrel per day also in full form. Okay, so all are valid. Oil gravity is given. Oil gravity 33 degree API. Okay, so that means it is a light oil zone, okay, medium or light oil. All right. Oil gravity is there. Inlet temperature is given. Inlet temperature is given 70 degree Fahrenheit. And treating temperature, operating temperature they have given T operating temperature. So I am writing just TO. Okay, 130 degree Fahrenheit. And some assumption they are asking to take, like specific gravity of oil, specific heat capacity, not specific gravity, specific heat. Oil is 0.5 British thermal unit pound mass degree Fahrenheit. For water 1, the same unit. Okay, and efficiency also they have given 70%, means 30% energy loss is there. Okay, previous day we calculated for 10%, but they have given 70%, means 30% loss. Okay, so now oil, Q oil solution. Okay, so solution Q oil equals 301. I'll say how 301 I'm getting. LBM BBL 0.5 130 minus 70 and 41.7. Okay, how the 301 I got? Actually, first you have to convert the specific gravity 33 degree gamma O, specific gravity 141.5 131.5 plus API. Okay, so you are getting here 0.8628602. Okay, 02. Now if you convert to lbm per per barrel, yeah, per barrel, then that will be converted into 301. Okay, that is density. Okay, lbm per barrel. Okay, so this conversion you should remember, actually very difficult conversions, but you should try to remember. Then Q water, so this will be giving value 337. Okay, better I'll write like 337,551 British thermal unit per hour. Okay, Q water also you calculate same way. So it will be instead of 301, it will be coming 3501 into again 130 minus 70, it will be coming 60 into 0.2, and the last digit 41.7, it is coming like barrel per day is given like 1000 divided by 24, it is coming like 41.7. Okay, 1000 barrel already given. So in water case also you have to convert the 20, not 0.2, 20.8. Okay, so this value will be coming 1161930 British thermal unit per hour. Now if you convert into per year, how much total energy you are giving, then per hour into 24 into 30 or 365 you have to multiply, then in that way you are getting 1.02 into 10 to power 10 British thermal unit BTU per year. Okay, this is this much of heat you need. Okay, now if you know the price, okay, so some example price is given, but present price may be different. In the book, whatever price is given, I am trying to calculate that one. Heating value of gas, heating value of gas, okay, because 1000 BTU per SCF, standard cubic feet. Cost of fuel, cost of fuel gas, they have given like 1.75 MSCF. I don't know, the same price is still there. Okay, so total estimated heat cost, will be $17,850. So just you can calculate and you can get this much of money. Okay, later we will see how electrostatic treater will help to reduce this cost. Okay, okay. So whenever you are heating, so oil will be shrinked. Okay, so oil shrinkage. So this, there is one curve, temperature, oil, wait, okay, oil shrinkage. So oil shrinkage, 0 to 3% shrinkage possible, and API gravity, API gravity. Okay, API gravity loss. So oil for different 1, 2, like 40 API, 30 API, 20 API. Okay, and loss of volume. You are increasing temperature, so volume will be lost. So temperature, it will be like 50 to 180. They are giving 1 to 3. So you can see the temperature increasing, your volume also changing. Okay, and specific gravity, how it is changing, T, the specific gravity 1 to 0.825, lower actually, so it is coming like this. So the specific gravity also changing with increasing time. Okay, and BSW changing, this is time, BSW 0 to 12, conventional system 30 minute, 0 minute, 30 minute. Okay, and this is conventional, and this is electrostatic, BSW, this will be conventional, settlement. Okay, so you can see in this figure, conventional will have more time to settle, conventional, and this is electrostatic. Okay. And how this electrostatic separator will be placed, electrodes inside a separator. Okay. Uh, we have to make like this, and oil is here, heater treater, it will be giving heat here. Okay, normally there will be flame arrestor. Okay, this is heater treater pipe, and water will be deposited here, and oil will be going out here. This is oil. Okay, this is gas, there will be one gas out, and here you are putting electrodes. Okay, electrodes. Okay, and here you are spreading properly, spreader. Okay, whatever fluid is coming here, it will be deposited here, then you are spreading from here, properly spreading, so that electrode will get almost equal everywhere this water particle. Okay, and you are putting electrode on the upper side. If you have very sparsely distributed particles, small particles are distributed, so you are putting here. Okay, and you are collecting water here at the bottom, and if you are creating wear or something, then water oil you can collect from here. Okay, because in between center portion there will be electrodes, so the electrode will be separating oil and water, and top portion water you can get, oil you can get, water will be settling bottom, you take from there. Okay, this will be simple. This is fire tube. So fire tube means there will be one firebox. From firebox you can give direct heating or indirect heating. Okay, we'll discuss electric versus thermal treater or electrostatic versus thermal or heated treater. How electrostatic system is helping, we can discuss. So electrostatic treater reduces maximum temperature. This is reducing maximum temperature, reduces. Okay, so when it is reducing maximum temperature, that means fuel consumption also going down. It does not affect viscosity, does not affect viscosity of crude oil. Okay, give lower shrinkage, because temperature is lower, so shrinkage is lower. Shrinkage lower. Low API gravity loss, low API gravity loss. Around 40-degree temperature, lower temperature possible. Temperature reduction of 40-degree Fahrenheit possible. Okay, and for 20 to 35 API oil with moderately stable emulsion. Okay, now we'll try to solve one problem. We'll try to see how much saving possible. Okay, so previously we have seen one problem of heat duty calculation. So same problem if you want to solve with electrostatic separator, where temperature rise 40-degree, the maximum temperature reduced by 40-degree. So then what will happen? Max temperature or separator temperature, temperature reduced by 40-degree Fahrenheit. So in that case, Q oil, from previous formula we can get 125,517 BTU per hour. Q water 145,600 BTU per hour. So total Q 387,310 BTU per hour. Okay, this will be 3.39 into 10 power 9 BTU per year. Okay. So, total heating cost equals 5932 per year. Okay. So, assuming like 1.75 standard cubic feet of fuel gas. Okay. So, estimated saving let's say VING, estimated saving is 17812 minus 5932, so it will be like 11879 per year, okay, because of temperature reduced. Now, if we calculate the shrinkage and other parameter also, then this saving will be further lower, as further higher. Now, we will discuss electrodes. Okay, electrode spacing will be normally 3 to 5 inch. This one thumb rule is there. So, electrostatic can reduce water 0.2 to 0.5%. Okay, so low reduction possible in BSW, BS and W. Okay. Now, attraction force between droplets. Attraction force between droplets. Okay, the force is equal to Ks epsilon square dm square by s power 4, where with s greater than equals dm. Okay, K is constant, F is attractive force between droplets, force between, okay, epsilon is your voltage gradient, dm particle diameter or droplet diameter. Okay, and this criteria should be satisfied, s greater than equals dm. So, if we have, let us say, s part also have given distance between droplets, distance between droplet. Okay, so distance between droplet increase, in small increase, the attractive force drop in attractive force will be very high, because you see power 4 is there. Okay, s power 4, dm power 2. So, dm small increase, it will be increasing attraction force, but if you are increasing s4, then actually it will be reducing attractive force very high level. So, whenever you are seeing the particle size located at very long distance, then attractive force will be very smaller. Maybe in that case you have to apply more voltage gradient, so that you can get sufficient force to attract one particle by another. Last topic of this one is droplet size. Okay, already you have seen Vt proportional to dm square. Okay, so particle size high means settlement rate will be high. So, oil water interface zone, where all coalescence normally will be occurring, it will be assumed and it will be happening also. So, temperature effect on water droplet distribution is small. Okay, so temperature effect on water droplet, small, but it is high for oil viscosity. Okay. So, normally retention time will be like in electrostatic separator 10 to 30 minute. Okay. So, if you have changed viscosity and density, water viscosity density not change, using electrostatic separator you can get better separation, and the electrostatic separation can be assisted by heater treater and other mechanism. Thank you very much for today's lecture. Next day we will start new topic.